Hello, everyone. This is Kyle Welch with RCR Wireless News. I want to thank everyone for attending today's webinar, Validating the Performance of Cellular Networks with Cpri Fiber Interfaces Between Ground-Level Baseband Units and Tower-Mounted Radios, presented by Anritsu. Our presenter today is Emilio Franchi, Product Manager at Anritsu. At this time, I'd like to pass the presentation over to Emilio.
Thank you, Kyle. And thank you, everybody, for attending. As Kyle mentioned, my name is Emilio Franchi, Product Manager for Anritsu, and we'll be talking about making RF measurements over the Cpri interface. So first, I'll cover a few things. Where does Cpri fit in? A little bit on the protocol stack, SFP data, layer 2 alarms, the differences between traditional RF and Cpri. Key parameters, setup configurations, filtering, and then we'll get into the measurements. Basically, all of these things, to be able to do a good measurement, you have to have everything working properly. So where does Cpri fit in today? So traditionally, we had our old towers where you ran coax up the tower from the node all the way up to the antennas. So everything was down below. You ran coax, and maybe you had TMAs up there. And then what's typical today is now that we have the BBU down below, we're running optical fiber up to the RRU or RRH up at the top of the tower with the antennas. And this is today's typical setup and what we'll primarily be talking about today. And where we're going is what we call a CRAN network. So that's basically where you have the BBUs in a centralized location, and then you have the RRHs distributed through a fiber ring, typically a WDM type of ring called CRAN. So the Cpri protocol stack has two main layers. The first one's the layer 1, the physical transport. So that's basically your optical transmission over fiber. It can be over single mode or multi-mode. Single mode is usually used for long runs in like the 10, 20, 30 kilometer range. Multi-mode is short runs. In the past, multi-mode was used for those short tower installations because of the cost difference. I think that's come way down. So I've seen a lot more single mode used in the BBU up to the RRH on a tower. The layer 2 is where you start looking at your L1 in-band protocol, and for what we're really interested in doing, IQ data. So the IQ data is within this layer 2, and that's what we're going to be using to look at RF spectrum type measurements. And in this, I don't know if you can see my mouse moving, but your radio equipment controller, that's your BBU. Radio equipment, that would be your RRH in green. This is just a typical configuration. You have your RRH that's coming down fiber optics to your BBU, and you have some type of optical tap that you can plug into your test equipment. Okay, so also wanted to get into, why do you care about Cpri RF measurements? So one of the key things is really lowering OpEx costs, operational expenses. So right now, many carriers don't allow their technicians or engineers to climb towers and connect up to the RF inputs of RRH to make any types of measurements for interference and so forth. So they end up calling a third party or tower crew. So there's a cost for just bringing a tower crew out to the site, additional costs for actually doing any type of work that's necessary. So the idea of using the Cpri link is to basically make measurements at ground level and then make a determination if you actually need to call in that third party. So that's one of the key benefits of Cpri is the fact that you can do those measurements at ground level, look for interference, possibly look for PIM, and then make a decision on to whether you need to call somebody in or not to climb the tower. So one of the key things that you want to make a good measurement is you got to use the proper SFP or transceiver to make a proper connection with the rest of the Cpri link. So normally for single mode systems, you're going to run into a 1310 of wavelength, nanometer wavelength. And if you're seeing a 1550 nanometer wavelength, it's typically a multi-mode SFP. Also, there are multiple rates, which I'll cover a little bit later. So for example, the most common ones today are rate 3 and rate 5, which is 2.5 and 5 gig. So if your system is running a rate 3, then you got to make sure your SFP covers that range. Otherwise, you're not going to get any proper connection. You just get a flat line on your spectrum when you're looking at the spectrum. So something like a tool that allows you to plug in the SFP and then read it on the instrument and verify that, yes, this is the correct wavelength and it's correct bit rate supported for the measurements I need to make. And then that goes also after you've made all the connections, and now you want to verify that you actually have a good connection. So you're looking at your layer 2 alarms, which is part of that protocol that we looked at earlier. So you want to make sure you have your no signal loss of a frame or sync or so forth. So if all the lights are green, then you're good. One of the things that also you need to make sure when you plugged in your SFP in your test gear is that it's seated all the way in, because that's happened to me in the past where I didn't have it plugged in all the way, thinking I was going to push it too far. But it's had enough to see some of the signal, but not all. So make sure it's pushed in all the way. One of the other things that's critical is your optical jumpers. They're very fine, so you have to be careful. You're not going to be breaking them. If you're used to working with RF cables, you tend to manhandle them. Optical cables, you can't afford to do that because they'll break very easily. And once they're broken, you're not going to get, you basically lose all connection. And the other thing that's important is cleanliness. So similar to PIM, make sure that all your connectors are cleaned and that you're using the proper cleaning tools for fiber optic cleaning tools to keep both the connectors and the fibers clean. And you can also use a visual inspection probes to validate that everything's working properly. So there are some differences between Cpri and RF. RF is basically, once it gets transmitted, it's an analog system. Cpri in digital, in the sense that it's raw ones and zeros that are coming up the transport pipe on the fiber optic link. RF is an absolute measurement. Cpri is really relative. It's all baseband information. So RF, you're seeing dBm. Cpri, you're seeing dB. In RF, you also tune to a specific center frequency. At Cpri, it's frequency agnostic in the sense that everything comes down at baseband. So you actually have to manually input the frequency that you're trying to make a measurement for if you're trying to capture a screenshot for that. And again, like I mentioned, relative power levels over absolute power levels. Also, you're going to be looking at only a single carrier on Cpri normally, so or a span that includes the carrier plus a little bit more data, so that you're going to have a limited span. And so compared to an RF spectrum analyzer, which lets you widen out as wide as you want, you won't have that same capability with Cpri, just because of the limited amount of digital information. So some key parameters, line rate or option rate. So this is basically the speed of the connection. As I mentioned before, the most common ones today are 3 and 5, 2.5 gig to 5 gig. The antenna container. So the antenna container is where the IQ data is for the individual carriers. So each individual carrier will have its own antenna container. I call it Cpri bandwidth, so it's basically the bandwidth of your, in this case, LTE carrier. So, 1.4, 3, but the most common ones are 5, 10, 15, and 20 megahertz. Your IQ bit width, again, there's multiple values there, but the most common ones I've seen with different radio vendors have been 12 and 15. And I'll talk a little bit more about the IQ bit width in another slide. And the reserve or stuffing bits, again, it goes from 0 to 10, but or beyond. But in reality, the most common values are 0 and 6. And then what we're calling Cpri aggregation, there are some vendors that actually will, and this is not carrier aggregation that's done over the air. This is actually aggregation of smaller Cpri antenna containers that are combined to create one larger antenna container. So, for example, 2 5 meg carriers get combined into one 10 meg antenna container. So the Cpri bit rates, I think there's a lot of terminology out there, line rate, bit rates, options. So they go, the Cpri standard 6.1 just came out recently, and it added a couple more. So there's actually 10 rates now. Like I mentioned before, line rate 3 and 5 are the most common, but I do know there are trials with 7 out there. Some folks are going to go to 8 for some trials. So just talking a little bit about the line rates, there's different types of encoding, the 8B, 10B, which is from line rates 1 through 7. That gives you a little bit more of security. And line rate 64B, 66B is more for speed. By the way, the link I have up here, the cpri.info, that's actually the website for the Cpri, where you can get the Cpri specifications. So Cpri parameters, antenna carrier. So that's what we call the AXC. So that's really where the IQ data for a specific carrier is, and you want to find it for a specific bandwidth. And then there's different mapping that determines how that information, that IQ information, is mapped within the antenna carrier. The Cpri bandwidth, again, that's basically what your LTE carrier bandwidth is. So if you have a 10 megahertz carrier, that's what you use. If you have a 15 meg carrier, that's what you use there. So it's pretty basic information, but it's this is the key parameters you need to know to configure a Cpri link if you don't know it ahead of time. The IQ bit width or sample width, this is basically the width of the IQ data within the frame. So like I mentioned before, the standards go from 8 to 20 on the downlink and from 4 to 20 on the uplink, but the most common values I've seen are 12 and 15. So those are the ones that, and they're not going to be the same for the uplink and downlink in most cases. So sometimes you'll see one value for the downlink versus another value for the uplink. And then when you have a smaller value below 15, you usually end up using what they call reserved or stuffing bits. So that gets into basically filling in the rest of the frame, so you're sending a complete frame full of data out. And as I mentioned before, the Cpri aggregation, you're actually combining two smaller AXC carriers into one larger one. So 5 meg, two 5 meg AXCs will combine into a single 10 meg AXC. Okay, one thing that's just wanted to kind of call out here also on a traditional, let's say if you have access to the RF input port on, especially if you're on top of a building, you may have access to that. And when you plug into your input, your tap for RF tap on RRH, then you would have access to basically the full filter of the RF filter. So you may have your carrier in the middle, and then you may actually have an adjacent signal that could be interfering because it's being allowed in through the filter of the wider filter of the RRH. So that's common so you're looking at in-band and out-of-band within the filter range of your radio, and that's very common on the RF side. But when you get to Cpri, there's also a digital filter that happens right before all the IQ data is sent down, and basically it strips out all of that out-of-band information. So you're only going to see the in-band carrier information that's coming down the Cpri link. So there is a limitation in the fact that you're only going to be doing in-band testing for Cpri. And what I have here is basically a picture of one of the taps I typically use. In some cases, there'll be an integrated tap already at the network, but it varies. And so it's always good to have your own portable tap to take with you. So there are different taps out there. These are just mine. Normally, single mode is going to be yellow. Multi-mode is going to be orange. And the cables typically follow that. But when you go into a site that's got the more armored cables, you usually don't see any colors. It's usually black, or they use something else. So the next one, I'm going to follow up with a connection slide here. So this is your typical configuration. When you see I don't know if you see from the RRU, the dotted line to the SFP, that's your normal connection. What you need to do to plug in is, well, two things. One is make sure you lock down the sector, but also when you're doing this, you've got to follow proper procedures, whether it's in the maintenance window, or if something's already wrong, then you may be allowed to lock down the sector for a few minutes during normal operating hours. But that's basically going to be case-by-case basis, up to your company's rules. But the idea here is to disconnect the cable that's going from the RRU to the BBU, plug that into your A tap in the optical tap, so the A port. Then you want to run a duplex cable from your B port to the SFP and the BBU, and then you can actually unlock the radio and then have live traffic streaming through again. You can also validate that really easily by seeing that the BBU light turns green again. And then you have an AB tap. Those are both output taps. So basically the A would be your uplink, and the B would end up being your downlink, so you're looking at the BBU traffic. And in this case, you would just use a simplex cable going into your RX SFP port on your test gear. And you switch that back and forth. And again, keep connections clean. Also make sure you're not stressing the cables too much, because that could cause some problems. And this is more step by step, so this is more for your reference, so you can kind of go through your little checklist. And you know, if you're going to go out there in the field and you're going to make some of these measurements, it's a kind of a quick way to kind of reference how you're going to do it, whether you use this tap or some other tap or anybody's gear. That's just some of the things you should think about. So once everything is working, you're going to actually see a spectrum, like a display here. And if you don't have everything working, you're going to have a flat line. It's basically digital. It's either on or it's off. So to make it a little more interesting, I actually have some videos. So I'm going to run this video. This is actually a BBU spectrum. One of the things you'll see is the nice slope, kind of rounded slopes on the edge of the signal. That actually will give you a good hint that that is the BBU signal you're looking at. Also, remember the control channels on a BBU side are going to be, for LTE, are in the center, 1.4 megahertz. So you may see a lot of activity there. This is actually, I believe this was at a toy cell. And this is actually a toy cell for the RRU. And you'll see some, so now we're looking at the uplink, and you can tell the difference because on the uplink, your control channels are going to be on the edges. So you may have, like, they look almost like little horns as they pop up a little bit when you get some traffic up there. So this is actually a toy cell without a lot of traffic. I have one more video that shows a live traffic signal. And this is, by the way, my amateur iPhone video here. And here we have live traffic, and you can see the resource blocks popping up and down. And so this is a site where we had pretty significant traffic going on. The other things you're looking for, so you're looking at your spectrum analyzer, you're looking for interfering signals, any signals that shouldn't be there. One of the key ones also is PIM. So this is actually a screenshot from a real site. And they captured this in what they call the Sharkfin shape. And really what's showing is you're transitioning from the IM3 to the IM5 on your PIM. So that's why you get that slope. So at certain frequencies, that'll happen. The other things you can do is, again, if you're in the maintenance window, you can always turn on OCNS and see if your receive band goes up as you turn on CNS on. So that would indicate that you probably have some type of PIM going on, because a rise in your downlink should not necessarily cause a rise in your uplink. And that's, so it's a decent indicator. The other one is, like in this case, live traffic. You see it and you're actually seeing a real PIM signal. Now, you may have intermittent interfering signals. That's when you start using something like a spectrogram. Again, through the Cpri link, you can set it up to look at it over a specific amount of time on a specific antenna container. And then you're just tracking to see if there's a specific signal that shows up, or it's a bursty signal jumping around that may be interfering that's on top of your carrier. So there's many things they can do this. Cell phone boosters that a lot of folks like to put into their offices, small offices. Things that are temperature sensitive, vehicles as they're passing by, especially now that everybody's got a Wi-Fi hotspot in their cars, that could cause interference. So things like that is what you want to try to see with a spectrogram. And then we get into RX diversity. So in this case, what you're trying to do is look at multiple AXCs at the same time. So you're looking at the two MIMO antennas, or your received, which is also your received diversity, and you're comparing the levels of the or the loading of one sector versus the other. So it's a real quick and simple way to do that. You can also do that for a multi-band setup where, let's say, for example, you have an AWS and a 700 megahertz system, and you can actually then compare the levels of the two different bands to make sure your loading is relatively even or not, depending on how you have it engineered. So it's so Cpri does allow you to do some additional measurements based on that. So to summarize, so Cpri measurements require a live signal, allows you to measure at ground level, make sure you keep all the connections clean and your fibers in good shape. Match SFP rates throughout the test link. Validate your connection with layer 2 alarms. Check for you're going to be looking really at in-band interference, whether it's external PIM. Also can be used for testing diversity, multiband loading on your system. So thank you very much. We're going to go to the QA session.
All right, thank you, Emilio. So we've had quite a few questions come in, and for any other questions anyone has, please use the QA panel, and we'll get to those. So first one that came in, it's a easy one. What is SFP?
So I know it's standard format. I always forget the whole thing, but it's a standard format plugin. It's a standard format plugin device is what it stands for. So they come in different, they come with their own built-in lasers. So they each have different wavelengths, and they're also rated for different data speeds. So that's when we talk about line rates.
Correct. Okay, so next question we had come in, what are the most common causes of failure in the Cpri link?
Honestly, it's probably going to be dirty fibers. So a lot of folks, you know, it's really easy to forget to plug anything. As soon as you open up the fiber, it's exposed to the air. There's dust in the air. So all of those little things will get inside the tip of the cable, and then they will actually cause blockage on the fiber. So it's really important. That's why it's really important, and I guess stressed it a few times, to make sure you have everything clean. Use your visual inspection probe, validate the fibers is clean. The other one's also possibly the SFPs aren't not matched correctly, so that you don't have the same SFPs at the RH as you have at the BBU.
Okay, next question we had come in. Will technicians using Anritsu's new Cpri test features need or benefit from instructor-led training?
As far as I know, they will benefit from it, because then they can get a hands-on training. We have our field application engineers, and I believe we will have also a certified class. But yeah, the field application engineers are happy to help out and do things in person, because this is one of those things. Cpri is one of those things that, like I mentioned before, you have to do it in the live system. You can't really do it on a tabletop. So, and to be honest, the best way to learn is actually to, as they say, learn by doing. So you're connected directly.
Okay, great. So we have another definition question. What does OCNS stand for?
So I don't know exactly. Basically, what you're doing is you're going to full power on your LTE carrier. I don't know exactly what the OCNS stands for as far as the nomenclature, but basically it is you're turning on your LTE traffic at full power and transmitting full power out of the downlink side.
Sounds good. Next question. How common is it to have built-in optical taps on site?
It varies. I think it's, you know, every carrier's a little different. So, you know, and so there is an additional cost to that. So depending on if they see the value, then you can see it. But right now, I've seen it a few places, but it's not very common right now.
Okay. Next one. How easy is it to install an optical tap?
It's actually very simple. It usually takes us about 2 to 3 minutes. Again, you end up you have to lock the radio down, because you don't want to cause any problems there. And you unplug the fiber optic duplex cable from the SFP on the BBU. Plug that back into your optical tap on the A port. Plug your duplex from the B port into the BBU, and you can actually turn it on at that point. And then you have a live network, and then you can take your time, because the 2 output ports act more like a monitor port, so it's like an attenuated optical port. So you can actually then just plug in at your discretion whether you want to look at the uplink or the downlink.
Okay, great.
And by the way, I got corrected. So SFP stands for small form factor pluggable. Thank you very much.
Great. So we had another question come in about the Cpri tool. Can it show power levels for specific LTE signals and channels? And what about the resource element grid?
So the channel, so again, it's right now in dB. I know there's some folks that are trying to do dBm conversions, which are really more of an estimate because there's so many variations on how you can do that with both the radios and if you're trying to do it from the digital chip, there's so many different radios out there that's a little bit harder to do. The resource elements, you're looking more at the downlink measurements, so now you're getting into LTE DMOD scenario, but you're really only looking at what's coming out of the BBU, so you're not really seeing what's getting converted from IQ and then transmitted over RF from the RRH. So I always recommend for that type of measurement to still go outside with an antenna and do an over-the-air measurement.
Okay. Next question we had come in, what is the best way to find out if the interference caused by a PIM issue or an external signal?
So PIM, depending on the band, PIM can be pretty, like that's 700. That was the Sharkfin was around 700 megahertz band, so that was pretty easy because you can see the transition. So you know that's a PIM issue. The thing normally so I think that the key thing with Cpri is trying to find out if there is something there to then call the tower crew up, because to actually find out if the PIM is internal to your system or external, you'd have to still go up to the RRH, connect a PIM tester, and then go through the process of doing a distance to PIM measurement to find out if it's within the antenna system or beyond. If you're looking to see if it's something else beyond that, hopefully it's not. If it's a wideband signal, you may see the whole noise floor rise up to you'll see the in-band signal rise. So again, you're looking for combination of performance parameters on as far as how many users are you having compared to how much output power or input power you're seeing from the receiver, and what's your coverage area. So you still would probably at the end of the day make that call and say, I need to have a crew out on at the radio and then connect up to finalize what type of interference it is. If it's something like a narrow band signal, that's easier to pinpoint because then you can actually zoom in on it with a marker, zoom in and kind of make a determination where it is from a frequency standpoint, and then actually go out with a spectrum analyzer and a Yagi antenna and try to narrow that down, because at least you know which sector it's coming from. So it's not a cut and dry thing. I think it depends on each signal's different, and each situation is going to be a little bit different. So you'll either have to climb the tower, or you'll just grab a spectrum analyzer and then use your tools for interference hunting.
Right, great. Good point there. Is it possible to take RL or DTF measurements through Cpri?
So it's possible. It's possible if you get the help of the OEM vendors. So they have what they call the CNM, the command line information. So if you have access to all the different vendors, then yes, you could do that. But that's not the easiest thing in the world to get. That's proprietary. Actually, the Cpri standard actually has a whole section that says proprietary vendor specific proprietary data. So if you do go into the Cpri.info and look at that in there, you'll find that section.
So also on the Cpri tool, can you determine an absolute dB value with the Cpri measurement?
So again, a dB value you can. dBm's a little tougher. So remember, absolute is dBm. Relative and relative is what we're looking at from a dB perspective.
Okay, great. So another question we had come in, this is back dealing with PIM. What is the cause of PIM in a Cpri system, if there's anything else to add to that?
It's basically any PIM source that can, it could be, again, dirty, you got metal shavings in your connectors. It could be a bad antenna that got damaged in transportation or with movement of the wind. It could be some type of metal external to the antenna system that's causing that you're transmitting into, and you're getting a reflection right back into it. So the the carriers are mixing and sending you back a IM3 or IM5 signal back through your receive band. So there's no, PIM is PIM, so it's just the fact that you're actually able to look at it through Cpri at ground level as opposed to having to climb the tower. But the sources of PIM are still the same.
Okay. So if you have Cpri panels with monitor ports, can you perform testing without affecting the service?
Yes. Because basically that allows you to plug in directly, and you don't need to lock down the radio at that point. So basically it's like, I always like to think of it as an old T1 or DS0. You plug into your monitor port and see what's happening without affecting what's going on in the service.
Okay, thank you. We had a question come up about the Sharkfin PIM that you discussed earlier. Can you go into that a little more detail and what exactly was shown on the screen?
Sure. So that was, let me see if I can get back there. So that is more of you're seeing a transition between the IM3 and IM5. It just happens to work at this frequency band. So the IM3 is your higher band. So when PIM happens, you get in the third order intermod is going to be 3 times the width of your main carrier or the interferers. And then it's going to be down a certain amount of dB. And in the fifth, it's going to be 5 times wider, but it's going to be even farther down. So what you're seeing is a transition happening between the third and the fifth. And in this case, it's because LTE is it's not a single carrier; it's a whole bunch of small 15 kilohertz carriers. So those 15 kilohertz carriers are actually mixing and creating the intermod problem.
So what is the typical distance you have seen and tested between the BBU and the RRU?
So for me personally, I think it's only been, I think 300 meters has been the longest for me, but you know, it's going to vary depending on each site. So that's, I think, the longest ones I've been to, but I know there's some that are, I think some of my cohorts have done like a kilometer or so.
Wow. So next question coming in, how much does the engineer tech need to know about the Cpri setup?
So it really depends. You need to know at least the vendor. So, and then we have, on our instruments, we have some pre-configurations based on that. If you know the bandwidth of the carrier, that really helps. We also have, for us, we have an auto-detect. So we actually auto-detect the line rate, and we'll look for the antenna containers. So that helps. The technician only need to know basically what radio vendor it is at that point. So Cpri can be a little bit difficult, especially at the beginning, but it really comes down to practice, and so we understand that we need to simplify the interface or the setup configuration for everyday use. But like I said, it's normally going to be if you have to do it manually, it's going to be the bandwidth, IQ bit width, your stuffing bits, your line rate, and then your bandwidth of the signal that you're looking at. And but in most cases, when you look at the radio vendor and you set it up for uplink or downlink, who I think most test equipment vendors have that, they already set up the IQ bit width and the stuffing bits for that. And then the line rate is something that either that can be measured manually or like in our case, we actually auto-detect the line rate. So it could be as little as a radio vendor, or it could be a lot more information. Okay,
we have a few more great questions coming in. So,
but by the way, somebody came in and told me OCNS is orthogonal channel noise simulator. So thank you.
Yes, great. Thank you for that. So how sensitive is a Cpri link to optical reflections due to splices, jumper cable, and other issues?
So it can be, but in those cases, you're actually using tools. I'm not as familiar because I'm an RF guy, but I've been learning on the job here. But you use things like your OTDR, so you're looking at your optical version of return loss in that case with those type of tools. So you want to look at that and make sure that everything's correct when you're doing that before you're looking at Cpri. But it can affect it because every splice is, it's a chance for something to get in there, and especially dust, for a better word, and cause some issues.
And we had another question come in. I don't think we've kind of faced it head on, but what is the maximum reach of Cpri?
So it depends on, there are other wavelengths out there that they're looking about for CRAN, and I believe you're looking at around 30 kilometers. But and I think that's what some, I'm trying to remember if it's 1560 or 1610 is nanometers, SFPs, or the lasers in the SFPs, but those are going to run really hot and really powerful. So, but as far as I know, that is about what I've heard, the max length around 30 kilometers.
Okay. Yeah, someone came in and said that the Supermax distance should be around 13 miles via fiber route BBU to RRH
Okay.
with a 190 microseconds delay in the fiber. So interesting. That's a pretty good reach.
Yeah, and for Cpri, that is what they're talking about, which again is some of the other test equipment, but round trip delay is a key factor in that. So.
Yeah, good point. Good point. So, is there any way to detect PIM on a DL band, not on the UL band?
In a sense, no. Well, not directly from the BBU, because you're really getting a perfect signal from the BBU. You're not seeing what's coming out of the radio. So that's something I think that when you look at the connection diagram, you're only looking at the output directly from the BBU box. You're not seeing what's happening after it gets to the RRH. So I know there are some tools that they'll use both the uplink and downlink to correlate things, but strictly from the downlink, no.
Okay, we have someone asking, do you have or know of a source for optical taps?
Yes, we sell them. We sell some. We do an 80-20 tap. So, and then there's if you Google, you'll actually find quite a few out there. You just have to know whether it's a multi-mode, single mode, or if you want both. And then what type of, like the 80-20 means 80% of the light is going through between the BBU and the RRU, and we're pulling 20% out for the testing purposes. There's also 50-50 taps out there, so you can decide which one you like to do. Okay,
a couple more questions here. So are you seeing this testing method being required on new build sites, or is it more for troubleshooting after a site has been on air?
It's both. I think especially, we didn't talk about it here, but it's what somebody alluded to earlier with the commands. It's basically, if you can get to what they call BBU emulation, then that's going to be what people want to use in new construction. And then what we're seeing now with the spectrum and the diversity testing, that's what you want to use probably more for troubleshooting existing networks. So it's a little bit of both.
Okay, so back to interference hunting. Can interference hunting be done with the same Cpri test unit, such as the MT8220?
So if you want to look things through Cpri and then nail down where the interferer is, and then go outside with a Yagi, the answer is yes.
Perfect. How do you explain the SFP mismatch in one transmission?
So if you have a mismatch, because this happened to me the very first time I ever connected to a unit, we grabbed all the SFPs that were lying around, and we didn't realize at the time until we actually measured them that they were line rate 1, the system was line rate 3. So we had a flat line basically. So if you have a mismatch, you probably won't see a signal at all. So like I said, digital on and off, that's basically how Cpri works. So if you have the wrong value, you'll have a flat line on the measurement screen. That's why it's always a good idea to test the SFP you're going to use for testing.
Okay. We had another question come in about the Sharkfin PIM. What do you mean by IM3 to IM5 transition? And isn't all IM present at the same time?
But they're present, but they are at different widths and power levels. So in a sense, that Sharkfin is catching it as a transition, as it goes from, I guess that's my wording, transition. As it's, so you're seeing an IM5, IM3, and then going down to a lower level to an IM5. So as you drop from a 3 to 5, you drop down quite a few dB. and I don't have the PIM. We have a PIM seminar, so I don't remember if it was 9 to 20 dB, somewhere in that range.
Okay, we have a couple more questions here. Does the Anritsu box have preset Cpri settings for specific vendor equipment?
Yes.
Okay. And then also, how can you tell between single mode and multi-mode cables?
Okay. That's a good question. Actually, I forgot to mention that. So in that case, you actually want to use, well, two things. If they're color-coded, it's easy. Yellow is single mode, orange is multi-mode. I've seen a lot that aren't color-coded. So this is where you end up using your visual inspection probe. And what you want to do is plug it in and then look at the core of the cable. So the core of the cable on a single mode is going to be much narrower than the core of the cable of the multi-mode. So if you have a jumper, for example, I end up having usually a single mode cables with me. I can compare that to whatever cable I'm looking at also, and then see if they match. If they don't match, then and one's bigger, then I know the other one's multi-mode. And so the way it's explained to me that the core of the cable is what in the center, and that's what actually transmits all the data. The outside is basically what holds, reflects back all the light so it doesn't escape and travels down the core.
Okay, great. So that's about all the time we have today. I want to thank everyone for attending today's webinar, Validating the Performance of Cellular Networks with Cpri Fiber Interfaces, presented by Anritsu. Again, our presenter today was Emilio Franchi, Product Manager at Anritsu. Thank you, Emilio.
Thank you, Kyle.